lecture series on differential equations for undergraduate students. Today's lecture is on solution of one-dimensional wave equation. In the last lecture, we had modeled one physical problem of vibrating string and we modeled it as a partial differential equations with boundary and initial conditions. Actually, we have got the partial differential equation as one-dimensional wave equation C square del 2 u over del x 2 minus del 2 u over del t 2 is equal to 0. And we have actually find it out the boundary conditions for this as u 0 t is 0 and u l t is 0 because the string was fixed at both the ends, and the initial conditions we modeled as initially the deflection u x 0 is f x and the initial velocity del u over del t at t is equal to 0 is g of x. Actually, in last lecture we had find out the solution of this boundary value problem as u n x t is equal to a n cos lambda n t plus a n star sin lambda n t sin n pi x over L, where this a n star are the constants which are to be established and this lambda n is nothing but c n pi over L, and this solution was holding true for n is equal to 1, 2, 3 and so on, even for some negative values of n also. We have also checked in the last lecture that when we try to find it out, that is whether this solution satisfies the initial condition so that we can establish this a n and a n star, we obtained that for certain values of x we are not able to find out the values of a n and a n star, that is in general this solution is not satisfying our initial conditions for all n. That says is, now let us see the solution of entire problem. For that we will first see this, that this given equation, this is linear with constant coefficient and homogeneous. So, using this fundamental result, that is superposition principle, we could say is that if I take the sum of this u n x t, that would also be solution of this problem. So, by that manner we are just getting the solution of entire problem. We let the solution u x t be summation n is running from 1 to infinity u n x comma t, that is summation n is running from 1 to infinity a n cos lambda n t plus a n star sin lambda n t times sin n pi x over L. Now, we try to satisfy this initial conditions. This lambda n we know is that c n pi over L. Try to see, that is when this solution is satisfying initial conditions. The first initial condition we do have that u x comma 0 is f x, and the second initial condition was del u over del t at t is equal to 0 is g x. Let us go one by one. U x comma 0 is f x, that means if I put t is equal to 0 over here, what we would get in this solution, if I put t is equal to 0 sin lambda n t, that is it would be sin 0 which is 0, cos 0 is 1. So, what we would be getting is here is only in this coefficient term only a n and sin n pi x over L. So, we are getting the u x comma 0 as summation n is running from 1 to infinity a n sin n pi x over L. Condition says that it must be equal to f x. So, it must be equal to f x. If I try to see is, that is what it is. For going for this entire solution of entire problem, we have to recall what we have learned about the Fourier series. So, here if we just see is, this is giving us a series that f x, this initial condition is saying is that f x is sum of certain functions, this sum of series. What is this series? This series is containing sine functions. So, actually this is a Fourier sine series we could say. So, what we just try to see is that we want this a n's such that summation n is running from 1 to infinity a n sin n pi x over L is same as f x. That says is, if I just use that formula of the Fourier sine series, we do get is that a n should be of the form 2 by L 0 to L f x sin n pi x over L dx. for all n 1, 2 and so on, using that Euler's formula for the Fourier series. Now, you see the Fourier series we have defined for the periodic function, but if you do remember, we have done the Fourier sine series where we said is that the function is need not to be periodic. Any function we are just making this extension, so odd extension and half range expansion, and from there we had obtained this formula. So, we say is that this solution u x t will satisfy my first initial condition if my f x if this a n can be obtained as the Fourier sine series coefficient of Fourier sine series of f x. Now, let us move to the second initial condition. Second initial condition is del u over del t at t is equal to 0 is g x. So, first let us find out del u over del t. Del u over del t, that is it should be thus differentiating with respect to t, we get it summation n is running from 1 to infinity minus a n lambda n times sin lambda n t plus a n star lambda n cos lambda n t sin n pi x over L. Now, evaluate it at t is equal to 0. T is equal to 0 says is that sin lambda n t, that sin 0, so it should be 0, and cos lambda n t, that cos 0, that it should be 1. So, what we would be getting is actually summation n is running from 1 to infinity lambda n a n star sin n pi x over L. Now, this has to be, according to this condition, this has to be equal to g x. Now, again what we are getting is the second initial condition is saying is that we should get this a n stars in such a manner that g x that this lambda n a n star is the coefficient of Fourier sine series of g x. That is, again we are talking about the half range expansion with the odd extension of g x. So, using that again Euler formula, lambda n a n star we want to be equal to 2 by L 0 to L g x sin n pi x over L dx. So, what we have obtained now, again lambda n is actually C n pi over L. So, we have got a n star should be of the form, because lambda n is this C n pi over L. So, we just take it this side 2 upon C n pi 0 to L g x sin n pi x over L for n 1, 2, 3 and so on. So, we have got that if we use this Fourier series and we use the superposition principle of linear homogeneous equations, then we can get the solution which is satisfying the boundary condition as well as the initial conditions. So, what we have got finally the solution, we have got solution as u x t summation n is running from 1 to infinity a n cos lambda n t plus a n star sin lambda n t sin n pi x over L with a n as 2 upon L 0 to L integral 0 to L f x sin n pi x over L with respect to x, and a n star as 2 upon C n pi times integral 0 to L g x sin n pi x over L dx. Lambda n is C n pi over L, and this is true for all n 1, 2, 3 and so on. So, we are getting this solution of our initial boundary value problem. Let us try to validate it, that is, does it really satisfies our equations. So, let us just try to see what this interpretation of this solution. For that, let us find out the exact solution. So, first we are, for simplicity, we are assuming that the second initial condition which is giving us initial velocity g x, that we are assuming as 0. Then we are trying to see can we find out the exact solution of our initial boundary value problem. It says as if g x is 0, then a n star, which is actually the Fourier sine coefficient of Fourier sine series of g x, because g x itself is 0. So, each one of that is coefficients would be 0, or we could say is that because that is integral involving g x, that would be 0, and my solution would be summation n is running from 1 to infinity a n cos lambda n t sin n pi x over L. Let us try to see what this we are getting with a n as 2 by L 0 to L f x sin n pi x over L dx. Now, we are having here is cos lambda n t, lambda n is C n pi over L, that says is we are having here is cos C n pi t over L, and this is the term sin n pi x over L. This a n is as constant. So, now we do not require this bracket actually, so because there is a single function. So, we are getting, let us just try to see what this function I could write, cos c n pi t over L and sin n pi x over L. Using the simple trigonometric formulas, we could write it out, that is, it is half of sin n pi over L x minus c t plus sin n pi over L x plus c t. Now, if I substitute this over here, what we get? We get u x t s, substituting instead of this this complete thing and breaking this series into two series, we get is 1 by 2 times one series, first series summation n is running from 1 to infinity a n sin n pi over L x minus c t plus another series, second series summation running from n is equal to 1 to infinity a n sin n pi x sin n pi over L times x plus c t. So, what this first series, let us see first series. We said is that is a n is 2 upon L 0 to L f x sin n pi x over L dx. We do know that if this is the a n, then the series a n sin n pi x over L, that is a n into sin n pi x over L, the series is sum is from 1 to infinity, is actually Fourier sine series of the function f x, or what we are calling it the half range expansion of f x with odd extension. Now, this in this series if I see, we are getting is a n as such, but instead of x we are having is here x minus c t. So, let us just write it as f star x minus c t. What is f star? F star is odd extension of f x. So, odd extension of f at x minus c t. Similarly, the other series also can be written as f star x plus c t. What this we are meaning by? Let us just try to interpret. So, what we have actually got, if I simplify the second initial condition with the initial velocity as 0 and initial deflection at t is equal to 0 as f x, we are getting the solution of our initial boundary value problem as 1 by 2 of f star x minus c t plus f star x plus c t, where f star is nothing but the odd extension of the given initial condition function f x. Let us see what it is interpreting. If you remember that we have started with one string that we had modeled. So, let us see that is its other way to that I do have our function, initial function, suppose initially the string is at this moment, that is at this position. So, I do have this the function f, its odd extension simply says is that f of minus x should be minus of f of x, that is whatever we are having over here, we just extend it to the in the reverse order in the second series. So, this is what we are knowing as the odd extension of f, and what we mean by f of f star x minus c t. So, suppose another function, I am taking another example. Suppose I do have f x function is of this kind, then if my x is starting from here, then f x minus c t would be starting from here. If my f x is starting from here, my f x plus c t would be starting from here. So, we are saying is that we have shifted it. So, we are calling it one dimensional wave equation. Why? We are getting the solution, if you do remember that u n x t we have got in the last lecture, the solution as a sine wave kind of thing, where for n is equal to 2, and if we are changing this time t with the time t, it is only shifting towards. So, that is why it is called one dimensional wave equation. Let us try to do one example where we are treating this some particular function f x. So, find the solution of wave equation c square del 2 u over del x 2 is equal to del 2 u over del t 2 with initial condition u x 0 as f x is equal to 2 k by L x and for in the interval 0 to L by 2, and interval L by 2 to L, 2k by L, L minus x. So, we do remember that we could just observe it that this is not a triangular wave, and the other initial condition that initial velocity is 0. We are not using here, the boundary conditions are same because it is being fixed over there. So, we are just trying to find out the solution of this wave equation. Already we had find it out that, so this boundary condition same as that, it is fixed at both the ends. So, u0 t is 0 and ult is 0. We had established that the solution of wave equation is summation n is running from 1 to infinity a n cos c n pi t over L plus a n star sin c n pi t over L times sin n pi x over L, where this a n and a n star we are finding out as the Fourier coefficients for the Fourier sine series of g x and f x. So, let us first see, that is because our initial condition gives my initial velocity to be 0, g x is 0. So, this a n star would be 0 for all n, and this a n. So, actually we will get the solution as containing only unknown function, terms a n's. This a n's can be determined as the Fourier sine series for the function f x. What is our f x is, this is also we had established. So, now let us try to see this function f x which is given to us, that is a triangular function. So, let us see that is what is its shape, and its this is what the function is been given to us, that is it is 0 to L, and at L by 2 it is increasing, and then after L by 2 it is decreasing. Its odd periodic extension means is if I go for the 0 to L, so then minus L to 0, this function should be just in the reverse order, this is odd extension. Now, we say is that this is periodic one, we are taking it up. Now, there is the functional form. So, a n we are going to calculate. A n should be 2 by L 0 to L integral f x sin n pi x over L dx. Now, substitute the values of f x in the interval. So, we have this, that we have to break up this integral into two integral parts, one is from 0 to L by 2 and another is L by 2 to L, this should be L. So, 2 by L as such, the function here is 2k by L is that is constant, 0 to L by 2 x sin n pi over L x dx plus 2k by L, L by 2 to L, L minus x sin n pi x over d, this one. So, a n would be integrating by with the by partition, first integrand minus L x over n pi cos n pi over L x evaluated from 0 to L by 2 plus L upon n pi 0 to L by 2 cos n pi over L x dx. Then the second integral L minus x. So, with the L 1 we have integrated it out, L is constant over here, the integral is L upon n pi cos n pi over L x evaluated from L by 2 to L, then minus x to minus x sin n pi x over L from L by 2 to L, again by with the partition L upon n pi x sin n pi over x n pi x over L evaluated from L by 2 to L, and the integral would be minus L upon n pi L by 2 to L integral cos n pi over L x dx. Again evaluate these values and solve those integrals. What we do get, 4k by L square is common, that constant, minus L square upon 2 n pi cos n pi by 2 because cos 0 is 1 plus L square upon n square pi square sin this integral n pi over x n pi x over L evaluated from 0 to L by 2. This evaluation is L square upon n pi cos n pi, this integral evaluation is L square upon n pi cos n pi by 2, this evaluation is L square upon n pi cos n pi minus L square upon n pi cos n pi by 2, and the last integral is minus L square upon n square pi square sin n pi over L x evaluated from L by 2 to L. Again these two evaluation we just go on and simplify the terms. We do get 4k by L square minus L square upon n square pi square times sin n pi by 2 minus sin n pi plus sin n pi by 2. We do know that sin n pi is 0 and sin n pi by 2 plus sin n pi by 2. So, we get it 8 k upon n square pi square L square is cancel it out sin n pi by 2. Sin n pi by 2, we do know that whenever n would be even, this sin it would be sin n pi and that would be 0. So, for even values, that is a 2 m would be 0 for m is equal to 1, 2 and so on, and for odd ones a 2 m plus 1 it would be 8 k upon n we are changing as 2 m plus 1 whole square pi square, and sin pi by 2 we are getting as minus 1 to the power, sin n pi by 2 is actually minus 1 to the power m with the odd ones. So, finally, we have got, if I just try to find it out, m is equal to 0, that is a 1 would be 8 k upon pi square, m is 0. So, minus 1 to the power 0 is 1, a 2 from here it would be 0, a 3 that means m is equal to 1, m is equal to 1, that is minus 1 to the power 1, that will give me minus sign, and here we would get 8 k upon 3 square into pi square. Similarly, a 5, a 4 would be 0, a 5 again we are going. So, m is equal to 2. So, minus 1 to the power 2, that is plus sign. So, we are just getting is that actually the series we are getting is 8 k upon, you could say is m square pi square for a 2 m plus 1 kind of thing with plus and minus signs. So, let us put it in our series and get the solution. So, we are getting the solution u x t as 8 k upon pi square 1 upon 1 square sin pi x over L, then cos c pi t over L, n is 1 here, minus 1 by 3 square sin 3 pi x over L, cos 3 c pi t over L and so on, we just go on. Again, if I just write this sin, you could say sin a cos b with the using the formula half of sin a plus b plus sin of a minus b, we would get it in the same manner, that is it is a half extension of f star x minus c t plus f star x plus c t, where my f is given triangular function and f star we are talking about just now, which I had shown that your odd extension, and we take it that it is periodic with the interval minus L to plus L. So, we had established this solution, this is satisfying our initial condition. Let us interpret this result. If t is equal to 0, u x t, you see that is here again I am coming up, u x t is this one, we want to establish it. So, let us try to see. If I take f star x minus c t plus f star x plus c t and 1 upon 2 over here, at t is equal to 0 we are being given this is the function from 0 to L like this one. Now, when I put this extension odd extension and add it up, we would be getting it the similar form. When t is equal to L upon 5 c we have taken, it is going in this manner, this is u x t, actually what if you see is in this manner, this is the function f star x minus c t. So, at t is equal to 0 it would be f star x plus f star x, that is it is simply f star x. If I am shifting it with t is equal to L by 5 c, that is we are shifting it towards L by 5, we would be getting it, that is it would be shifted towards. So, shifting means is now the function is starting from, this is minus 1 this is the plus 1 and this is the minus 1, that is I have to shift my origin from 0 to c t and 0 to minus c t. So, when we are shifting 0 to minus c t, we have to come over here, when we are shifting it 0 to plus c t, it would start at 0, the function would start like this one. In this manner, if I see, my u x t would be of this form. And if we are just going as L by 2, we are shifting it at the L by 2, you see is that is would be shifting the function plus c t, that means this manner, minus c t means this manner, this ray is coming over, this line is coming over here and this line is coming over here, and in that case my uxt would be simply this line. So, this is how we are establishing, that is what kind of solution we would be getting for this one dimensional wave equation. We just find it out that it is shifting ones. In this one, we had seen that the solution of one dimensional wave equation, we had find it out, we tried to use the product method, in which we had assumed that the two functions of x and t are separate, and then we find out the solution, changing them to the ordinary differential equations, then satisfying the boundary conditions, we find it out, and we find out that many functions are satisfying, then none of those functions in general were satisfying the initial condition. We use this fundamental theorem and said is that it is sum of all those functions, because the functions are infinite many, we had summed it as infinite many, and use this Fourier series tool and find it out that we could say is it is in the term of odd extension of the initial condition function, in which we are getting this wave equation solution. Let us see another method which we have done as using the characteristics, finding the type of the equation, and then finding out the solution in the terms of general arbitrary functions, and then try to find out that arbitrary function using these side conditions. So, let us first use this wave equation and solution. The name this D'Alembert solution of wave equation, that I will explain little later. The solution of wave equation, we want c square del 2 u over del x 2 minus del 2 u over del t 2. Now, just try to find out the characteristics and type of this equation. We have already come across this kind of equation, we do know that this is hyperbolic. Let us do it again to changing this canonical form. So, a is c square, b is 0, c is minus 1. This says is b square minus 4 ac is 4 c square, which is positive because c square is positive, 4 is positive. So, it is a hyperbolic equation. It must have two characteristics. The characteristic should be given by b plus minus square root of b square minus 4 ac upon 2a. b is 0. So, b square minus 4 ac is 4 c square. So, its square root is plus minus 2 c, and a is c square, so upon 2 c square. So, we have got the characteristic has been given by the equation dt by dx is equal to plus minus 1 upon c. That is, we have got two equations, dt by dx as 1 upon c and dt by dx as minus 1 upon c. If I integrate, we will get the two characteristic curve with plus sign. When dt by dx is equal to 1 by c has been integrated, we get ct is equal to x plus c1. The other one we would get ct is equal to minus x plus c2. Now, we want to change it to the canonical form. So, we will use the transformation using these characteristic curves. So, the first transformation we would use is x minus ct, another transformation we will use is x plus ct. So, we are transforming the new variables v and z rather than x and t. V is x minus ct and z is x plus ct. Now, change it to the canonical form, this given equation. So, we require del 2 u over del x 2 in the form of partial derivative with respect to v and z, and similarly the partial derivative with respect to t in the form of partial derivative with respect to v and z. So, we want to change it to the canonical form using this transformation v as x minus ct and z as x plus ct. So, first the derivatives, partial derivatives, del v over del x as 1, del v over del t as minus c, del z over del x as 1 and del z over del t as plus c. So, using the chain rule, we could get del u over del x as del u over del v times del v over del x plus del u over del z times del z over del x. Now, substitute this del v over del x and del z over del x, we get it is del u over del v plus del u over del z. So, the second derivative would be, that is del 2 u over del x 2, again differentiate del u over del x with respect to x. So, again using the chain rule, it is del upon del v of del u over del v plus del u over del z, because that is what del u over del x, into del v over del x plus del over del z of del u over del v plus del u over del z times del z over del x. Again substitute this del v over del x and del z over del x from here as 1, we do get it as del 2 u over del v 2 plus 2 times del 2 u over del v del z plus del 2 u over del z 2. We have assumed that the continuity of this partial derivatives, that is, we had assumed that del 2 u over del v del z and del 2 u over del z del v, they are same. So, we are getting this one. Similarly, let us get del u over del t. Using the chain rule, del u over del v plus times del v over del t plus del u over del z times del z over del t. Now, del v over del t and del z over del t, we are substituting from here, we get it minus c and plus c. So, we get it minus c times del u over del v minus del u over del z. So, again using this chain rule again on this one with respect to the t again, because we require the second partial derivative with respect to t, that we would get because here if you see is in this case also what we have to do is, that is, rather than using it x, we have to put it c, t. So, that is giving us again c. So, c square del 2 u over del v 2 minus 2 times del 2 u over del v del z plus del 2 u over del z 2. So, we have got this the both the derivatives with this one. So, now our given equation c square del 2 u over del x 2 minus del 2 u over del t 2 is equal to 0. This will change to, now we substitute this whatever we have got in the terms of this one, c square del 2 u over del v 2 plus 2 times del 2 u over del v del z plus del 2 u over del z 2 minus del 2 u over del t 2. So, let us put it in the right hand side. So, c square times this is what del 2 u over del t 2 del 2 u over del v 2 minus 2 times del 2 u over del v del z plus del 2 u over del z 2. So, we get on both the sides the terms involving del 2 u over del v 2, here is also the coefficient for both is c square. So, this will be cancelling out. Similarly, del 2 u over del z 2, the coefficient of this is c square here, the coefficient of del 2 u over del z 2 here is also plus c square. So, both these terms will also be cancelling it out. What we would be getting is, here the coefficient is plus 2 c square, here the coefficient is minus 2 c square, that means I would be adding it up. So, what we are getting is del 2 u over del v del z is equal to 0. Actually, we would be getting 4 times c square, 4 is non-zero constant, c square is non-zero constant. So, the final canonical form this differential equation we are getting is del 2 u over del v del z is equal to 0. Now, this equation, this partial differential equation we can solve using the integration one by one. So, let us go ahead with the integration first with respect to z. That says I would get del upon del v as h of v, because this is a partial derivative. So, when we are integrating, the constant integration of 0 is the constant, but because we have integrated it with respect to z, so the constant may involve the function containing v. So, we are getting is it h of v. Now, again integrate this function with respect to v, that says is I would get integral of h v with respect to v plus constant, that constant has to be can involve z, because we are integrating it this with respect to v. So, this may involve z. So, we say is that plus psi of z. Now, this is a function of z only, and here integral h v dv, this is a function of v only, because this we are integrating with respect to v only. So, we will get a function of v only. Let us write this function as phi of v. Then I could write it as my solution u as phi of v plus psi of z. Now, let us come back to the original variables x and t. The transformation we had used is v as x minus c t and z as x plus c t. So, changing back I would get the solution u x t as phi of x minus c t plus psi of x plus c t. This is the general solution of our one dimensional wave equation. Now, to find out the particular functions, that is what these functions phi and psi are, because this is a general arbitrary functions, we will use the initial conditions. The initial conditions given are that u x comma 0 is f x and del u over del t at t is equal to 0 is g x. So, first use this u x comma 0, that is phi of x minus c t, since t is 0. So, it would be phi x, and psi of x plus c t, since t is 0 it should become psi x. So, we get phi x plus psi x should be f x. Then we come to the second initial condition. Our solution u x t was phi of x minus c t plus psi of x plus c t. So, if I differentiate it with respect to t, first derivative with the derivative of phi x minus c t. So, here I am denoting it phi dash x minus c t, that what we are doing is we are using again the chain rule. This is the derivative with respect to x minus c t, the derivative of function phi with x minus c t, and the derivative of x minus c t with respect to t is minus c. So, we are getting is minus phi dash x minus c t. Similarly, for psi of x plus c t, we are writing this dash means the derivative of psi with respect to x plus c t, and then the derivative of x plus c t with respect to t is c. So, dash whenever we are introducing, it says is that the derivative of the function with that argument. So, del u over del t we have got as this one. Now, we have to evaluate it at t is equal to 0. So, if I am evaluating it at t is equal to 0, what I would get is here from here minus c phi dash x plus c psi dash x. This is given as g x. Now, we have got two equations, one is phi x plus psi x is equal to f x, another is minus c phi dash x plus c psi dash x is equal to g x. From here, this equation, let us because we are having is that this now derivatives which we are talking about, we are saying is with respect to that argument. Since t has been taken 0, this is the derivative with respect to x, this is also derivative with respect to x. We are getting this a differential equation in x only. We can just integrate it back, what we would get minus c times phi x plus c times psi x is equal to integral g x from x naught to x. Why we are talking about x naught to x? Because we have taken t is equal to 0. So, what we are assuming that at t is equal to 0, x is x naught. So, now just change the minus c I am taking common. So, what we are getting is phi x minus psi x is equal to k x naught plus 1 upon c integral x naught to x g s ds. Just to differentiate it, that is with this x and this x, I am just using that variable of integration as s. What is this k x naught? We do know whenever we would be integrating, we require certain constants. That constant has to be and that constant is being decided with the initial condition. Initial condition we are having is t is equal to 0. So, whenever t is equal to 0, I would get initially that x is equal to x naught. So, in that case what we are getting is k x naught would be actually phi of x naught minus psi of x naught. Now, we have got one equation over here, another equation from here. If I try to solve these two, what we get, if we just add it up, we get 2 of phi x is equal to f x minus k x naught minus 1 by c x naught to x g s ds, and if I just subtract the two ones, I would get 2 of psi x is equal to f x plus k x naught plus 1 by c x naught to x g s ds. Now, that says is these arbitrary functions phi x and psi x we have got in the terms of the initial condition, which is given as u x comma 0 as f x and initial velocity as g x. So, the initial velocity term we are using here is in the integrand, it is being coming as integrand, the integral of that function. So, now we see is in this method which we had used here to change it to the canonical form and then solve the differential equation, we had find out that the solution which we had obtained there. So, now if I just substitute this phi x and psi x in our solution, let us see that is what the solution we are getting. Our solution is u x comma t is equal to phi of x minus c t plus psi of x plus c t. So, now substitute this phi and psi. Phi is half of f of x minus c t minus half of k x naught minus 1 by 2 c x naught to x minus c t g s ds. We are putting phi x in the argument x minus c t. So, everywhere this x has been changed to x minus c t except that x naught, because x naught is the constant. So, here this integral is also from x naught to x minus c t. Then with the psi x plus half f of x plus c t plus half k of x naught plus 1 upon 2 c x naught to x plus c t g s ds. Now, just simplify it, what we would be getting is that these terms half of x minus c t, half of f of x plus c t. Now, what we are saying is x naught is initial point, that is we have started at t is equal to 0, x is x naught, c is positive, t is positive. So, minus c t would be negative. What it says is that this integral is actually the x naught to x minus c t, that means it is in the negative side. So, we can write using the properties of definite integral, we can write it as plus integral from x minus c t to x naught, and this integral is from x naught to x plus c t. So, both these integrals being added up again using the properties of definite integral, we get x minus c t to x plus c t, this integral of g s ds. Now, you see this solution is similar to that whatever we have got the solution of the entire problem in the previous section, where we had used the Fourier series, we had find out the solution using the product method. It was a lengthy process. Here we have got very neat and clean solution, but the thing is that this solution or this method of solution would be applicable when the function or when the equation is of such a form where I could change it to the very simple canonical form and we can integrate it out and we are getting as the exact solution. This is actually, this solution is called the D'Alembert solution of the wave equation. Does it satisfy the initial conditions? The boundary conditions, initial conditions, from the initial conditions we have got, does it satisfy the boundary condition? Let us see u0t from here, that is x is equal to 0, what I would be getting is f of minus c t and this would be f of plus c t, and this integral would be minus c t to plus c t g s ds. It should satisfy the boundary condition that says is I should want it to be equal to 0. This is equal to 0. Similarly, u l t half of f of L minus c t plus half of f of L plus c t plus 1 upon 2 c L minus c t to L plus c t g s ds. Boundary condition says that u0 t and u l t both should be 0. Now, let us see how this could be 0. What should be this my function f? This could be 0 if f of minus c t is same as minus of f of c t, that says is f is odd function. Moreover, this integral would be 0 if my g is an odd function, then we do know that integral minus a to plus a g x dx is 0 if g x is odd. So, the first boundary condition gives me, that is I should have my f and g both as odd function. Then let us come to this one. This says is this would be 0. So, again if I just try to use the similar explanation, I want that L minus C t, f of L minus C t should be same as minus of f of L plus C t, and again this function should be, this integral should be 0. Or if I combine this explanation of the first one with the second one, what we are saying is we want that this function whatever we have got, that is odd function from minus L to plus L, and then it should repeat, because after L minus C t, that is 0 to L whatever we had, we want that it should be odd, and then we want that it should repeat, that is L minus C t whatever we are getting, I should get it negative of that in the L plus C t. So, what we want is that my function should be odd and periodic with period 2L, both the functions f and g. So, what we are saying is this D'Alembert solution, as such it is very easy to find it out, but it is applicable in special conditions where this Fourier series solution which we had find it out, that was applicable everywhere, whatever be the function we could find it out, while as here we require that f must be an odd periodic function with the period 2L. So, that is what we are saying is this will satisfy the boundary conditions if f x and g x are odd and periodic with period 2L. This is what we have got the solution of first order second order one dimensional wave equation we had learned. So, now I just summarize, that is what we had learned in the partial differential equation. We had learned that is how to solve the first order partial differential equation, how to characterize them using the method of characteristics. We had find out that is the solution. In all the partial differential equations, we had find out that the solution is coming in the form of arbitrary functions rather than arbitrary constants, and those arbitrary functions must be decided by the side conditions. Those side conditions could be initial conditions or the boundary conditions, as in the case of as we had learned in the ordinary differential equations. Here we had learned that it may be a combination of both initial and boundary conditions. So, we have got one more kind of problem that we have called initial boundary value problem in partial differential equations. The second order differential equations, we had again learned the type of equation, the characteristics. Using those characteristics, we are changing them to the canonical form. We had learned that there are three types which are very important in theory of partial differential equations. They were hyperbolic, parabolic and elliptic. We have seen certain examples, we have done very simple examples of parabolic and hyperbolic equations. We have tried to model one physical problem which is turned out to be that governing equation is one dimensional wave equation which is hyperbolic. We tried to find out the solution of the complete problem, that is initial boundary value problem. We tried to find out with using the one method which is called the product method, and then we find it out that it was not satisfying the initial conditions, and we had gone to the method of Fourier series, and there we had find out the complete solution. Then we had done for the one dimensional wave equation another solution that we call D'Alembert solution, that was actually changing the equation to the canonical form and finding out the solution. There we had learned that it has little bit limitations than the Fourier series method. So, that is all in today's lecture. Thank you.